All right. Well, it's great to see that so many have found your way up into this building, to this little cinema hall to see me talk about CRUD and DDD. I know you all come for the CRUD part, right? So today we're talking about the evolution from CRUD to DDD. And while most of you are probably not as old as Gary in his opening keynote, who of you have created applications who you would consider to be CRUD-like? That's quite a lot of you. And who have created applications that you would describe as being kind of DDD? Almost a lot of you. Some less, I guess. Well, today we're going to talk about how this transition from CRUD to DDD came into place and what steps were taken along the way. So back in the old days, we have applications that we used to describe as CRUD. And CRUD comes from the different operations that you can perform on an entity. You can create them, you can read them, you can update them, and you can delete them. And it's not really coincidental that these are exactly the same operations that you can perform on a row in a database. Because that's one of the main characteristics of CRUD applications. The database has a very central role in them. Right? They were just almost a thin wrapper around the database, and the interface, whether that's the backend API or the UI, they're mainly just a thin wrapper around them. You have a UI that just looks like a database table, and then you click on a row, and you get a form that's almost like the database fields, and then you click save, and that it's just almost saves a row in the database. It's just a thin wrapper around these database central logic. What would a CRUD application back in the old days kind of look like? Well, you have this database, and you have two PHP scripts. This is really in the very old days, 20 years ago, I think. And, well, suppose we're creating a website for recipes or something. You would have a script view recipe that would get a recipe from the database and then just show it in the user interface. And if a user wanted to edit this recipe, well, it would just post data to an edit recipe script, and that would just do another SQL query to the database to save it. And I've only shown the read and update parts here, but you can imagine how a delete and a create kind of would look like. It's almost the same. And we can make this slightly more modern. This would be maybe 5, 10 years ago. You see all kinds of this stuff. You would then add in a framework, which has a front controller, which does all the routing for you. And then you have an edit controller and a view controller, and they talk to an ORM. So you don't talk directly to the database anymore, but you have kind of an object-oriented abstraction layer around it. But essentially, if you're just doing stuff like this, if your application is still a thin wrapper around the database, this is just CRUD in disguise. Right? Depending on how you're doing this, depending on how your ORM entities look like, this is still CRUD. We're just still doing creation, reading, updating, and deletion of entities, and our models and our UI still looks very much like our database. So you've been doing CRUD like this for years, and then your new colleague comes by and tells you about the new kid on the block, DDD, domain-driven design, which is awesome, and you should do that. And he says, well, we should speak in the language of our customer and put our business logic central and stuff like that. And you think, hey, that sounds like a good idea. We should talk in the language of the customer. Well, you're going to do DDD, in which the domain, right, the subject where the software is used, in my examples, creating a recipe website, so you would speak in the language of recipe makers and cooks and stuff like that. And, well, maybe publishers, because you're publishing your recipes. And the business logic in that domain gets a central role in the application, and the infrastructure is just built around that and is more pushed to the side. So you're going to start out with this new architecture that your colleague talks about. And what does that look like? Suddenly you get something like this. And right now you want to make a simple change. You want to add one property to your recipes, for example. Maybe a flag, whether it's gluten-free or something. And previously you just had to add one line to your model class. And right now you're editing 7 files across all these different parts of your application to just make this work. So I'm not going to go into detail into this diagram right now, But we will see how we could arrive at such an architecture. So that's the main question I want to talk to you about today. How did we end up here? And you can view this question both in a way how one single application could end up from a CRUD architecture to a DDD architecture, but also how we as an industry as a whole have evolved into this new style and how we made these steps that got us here. So before we start, just a small disclaimer. I'm going to show you some steps how you could evolve from CRUD into DDD, or how we have, as an industry have done that. These steps may be taken in a different order. You could leave some of them out. They may be executed differently, depending on how you interpret certain principles, how you choose your implementation, what technology you use. You've seen some color in my diagrams. For those who want to know, it's not essential. If you want to know, the blue parts are generic system-wide components. The yellow ones are specific to a certain feature or use case. So DDD is often used as a kind of an umbrella term. When people talk about DDD, it relates to a number of patterns and principles that all have to do with putting your business domain and your user's logic first. But there are a lot of things that are related to that, and they are used often interchangeably. So the italic principles here and patterns, we're not going to cover these today. They go either more in depth than we have time for, or they don't influence your architecture as much as what I want to show you. But you can see that there are a lot of principles related to DDD, and I will try to cover some of them. So to recap, we have our CRUD starting point for our recipe website. I've reordered it a bit to make space in the middle for all the new stuff that we're going to add. And suppose we have this recipe website and we want to add extra business logic. For example, that a recipe may only be published if they have at least one ingredient, because, well, it would be kind of strange to cook without any ingredients. If we would do this in such an architecture, we would have to add this business logic to these controllers, which are also talking directly to the ORM or the database. And that's pretty difficult to add, because we cannot test this business logic anymore in isolation. We have to test this using something that already uses the database. So to test this, we need a database, and our tests become slower and slower. This is not really a problem if we are just having one or two of these business constraints. But if we were to add maybe 100, we have 100 things that we have to test using a database. And our test suite becomes slower and slower. Tests become difficult to write, maybe brittle. So we really would want all this business logic to be testable in isolation from our database. Enter the aggregate pattern. So DDD describes an aggregate as a cluster of domain objects that can be treated as a single unit. So, for example, the ingredients in a recipe, they don't really make sense on their own, right? They are ingredients of a recipe. So the recipe is the aggregate, or the aggregate root as they are sometimes called, and the recipe includes their ingredients. And such an aggregate is responsible for maintaining the integrity and the business rules within that cluster. So a recipe is also responsible for its ingredients and the relation between the other properties. So we can say that the published property of the recipe aggregate and the ingredients property of the recipe aggregate, well, they have to be checked together by this aggregate to maintain this business rule. So we extract a recipe class as an aggregate, and that recipe class will just hold the business logic that we want to enforce. Rules like that a recipe cannot be published if it has no ingredients. We could add a rule that a vegan recipe cannot contain any dairy ingredients, all stuff like that. And we can test that in isolation from the database, because it's just a plain old PHP object that we can do tests on, and only then is it persistent into the database. So what this looks like is we now have a recipe repository that abstracts away our ORM. And from that recipe repository, we load, and after we make our changes, we save our recipe aggregate. And our recipe aggregate is now completely responsible for all this business logic and all these constraints that live in our business domain. From our edit controller, we just store all the new properties, right? We just post a form, and all this data, we save it on the recipe aggregate. And now the recipe aggregate can check, hey, okay, I see you want to have this recipe published. Does it have any ingredients? Oh, no, I'll just throw an exception. And what's new, we can test this using unit tests instead of testing using something that uses a database. So that's a big advantage of this approach. Now, what we see here is that we still provide the entire state of the recipe aggregate posted to the edit controller, and we provide all the data to the recipe aggregate. So that means that any change follows the same process, but we also always provide the entire state. And if two people change a recipe at the same time, for example, one wants to say, hey, this recipe is now published, and another wants to add an ingredient to it, these changes can override each other, right? If they almost make the changes at the same time, and one that adds the published flag goes just a little bit later than the one that added the ingredient, the new ingredient is lost. And also, it's quite hard to detect what changes our users want to make. They always provide, hey, here's your new state of your recipe. And we have to get the old one and see what changes are made between that to just figure out what is it the user actually wants, right? They don't want to edit a recipe or something. No, they want to publish it, or they want to add an ingredient to it, or they want to add a step. So because of this, a logical next step in this evolution is to introduce a command pattern. And a command pattern is described as modeling the possible actions or changes on such a domain aggregate and separating the intent from its execution. So instead of considering an edit action or something, we could have a publish action and an add ingredient action. So now we don't have a recipe edit controller anymore. We now have a recipe publish controller, which just calls a publish method on the recipe aggregate. And then that recipe aggregate just itself sets the necessary data properties or performs the necessary actions on its state to say it is published. Probably it's just, hey, this published is true right now. So this makes space to also add another controller for add ingredient and another controller for add step, which is talk to the same recipe repository, also call methods on that aggregate. But now the intention from the user is clear, and all these different commands are separated from each other, and if they were executed after one another, they wouldn't override each other's state. Still, we haven't really separated the intent from the execution, because now all the everything that signifies the intent is just the call to the recipe publish controller, but that's also the one who executes the publish methods on the recipe aggregate. So another problem with this is that we execute this action, this command, from our controller. And our controller is pretty much tied to HTTP, right? This is a controller that gets called by some router with HTTP parameters, post data maybe. And if you wanted to add a command line command to publish a recipe, we couldn't reuse the same code. So a logical next step is to introduce a separate command object and a separate command handler. And now our publish controller just calls the command handler with a publish recipe command saying, hey, I want to publish this. The user has, via HTTP, said that they want to publish this recipe. And then this command handler can do the rest of the stuff. And one advantage of this is that we can also add a console command, which calls the same command handler with a similar command. You could choose to not model the command as an object. You can just provide everything that's in the command as parameters to the command handler class. But we will see later why this is a useful case. But using a command handler, we've made possibilities to execute these commands from different sources, whether that's a console command, HTTP. We could add something that performs commands when an email is accepted. You could use a remote control device and execute a command if you click a button or something. this all becomes possible with the same architecture and reused logic. Now what's difficult in this architecture is that every command follows a different route. We have a publish recipe command handler, but if we were to add ingredients, we would also have an add ingredient command handler, and which is called from an add ingredient controller. And since they don't share a route, it's difficult to add generic functionality to all commands. Suppose we would like to perform every command into its own database transaction, or we have requirements that force us to log every command executed on the system, or we would want to add locking so no two commands can ever run at the same time. We don't have a single central place where we can add that. And the solution to that is to use a command bus. So a command bus is a one-stop shop to execute these commands, and you just provide your command to the command bus, and the command bus will look up the correct handler and deliver the command to it. So what does that look like? We just put a command bus in between, and that command bus also knows about all the other command handlers that are in the system, and anything in your system that wants to execute a command just provides it to the command bus, and that command bus will look up the correct command handler. Why is this useful? Well, right now we have all these sources of commands and all those handlers of commands running through the same thing, namely the command bus. So that also means that we have one single place where we can decorate that command bus. So we can wrap that command bus into a decorator pattern from the gang of 4 into a transactional command bus. And now that transactional command bus can start a transaction before executing the command by passing it on to the inner command bus, and then committing that transaction afterwards or rolling it back if something failed. If we want to add other behavior, we can decorate it again and again. So we can add logging in a central place, we can put all commands on a queue, all stuff like that. We can just decorate that single point in our application and have logic that applies to all commands. So this is what it looks like in the big diagram. We now have a single command bus that we can decorate with new behavior. So far we mainly talked about the edit side of the application. But look at the read side. The recipe view controller now uses the same recipe repository that we use to make changes. And that's fine for some cases, but not for others. Suppose we want to add a dashboard with a number of recipes for certain types of diets or something. All our updates, they always apply to one single recipe, but our dashboard involves a lot of recipes at once. So if we would do that through the same repository and through the same classes as we use for updates, we would have to load all these recipes, check their tags or labels or diet restrictions of however we call it, and count them to have our dashboard counters. So our read side sometimes does not really follow the same model or the same views as our update repositories. So here comes in command query responsibility separation, often called CQRS, and that distinguishes commands, the things that update the state of your system, from the queries which just read state from your system. And they treat these separately, and especially that allows creating specialized and optimized models for both. So if we want to add a dashboard, we can add a specific dashboard model. What does that look like? Well, right now, instead of only having one repository, we have a write model repository and we have a read model repository. And the changes from the write model repository are also communicated to the read model repository, which can then update the database with anything it likes. And our view controller just talks to the read model repository. What's the advantage of this? Well, suppose we want to have a dashboard. We can add a separate dashboard controller, which just talks to a recipe dashboard read model repository. Here we make a specialized read model repository for a dashboard. We can use a different data store for that. We can use a Redis cluster. We can use files on disk. We can pre-generate reports, anything we would like to support the dashboard use case. and we can just make these specialized models for all different views and cross-cutting sections we have in our application. What's difficult here still is the communication between the read model and the write model. You see here I've already added a question mark. How do we communicate these changes from the write model to the read model? We could just pass in the aggregate, but then we just say, hey, here's your state, and again, we don't know what was actually changed. We still have to detect, hey, oh, the published property was changed or something. So that is why a logical next step would be an event-driven architecture, where we use events, namely models of significant things that happened in the past, to communicate between the components in the system. So instead of the write model providing the entire aggregate to the read model, we just say, hey, a recipe with this ID was just published, right? And we can make these events, just like the commands, we can make them in the language of our domain. We can say, hey, an ingredient was added to this recipe. And by communicating these changes, we can synchronize the write model to the read model. So that looks something like this. Instead of passing on the recipe aggregate from the write model repository, our recipe aggregate now produces, once we call the publish method, it produces a recipe published event. And when saving that aggregate, our write model repository not only stores the state of the aggregate, but it also passes on this event that our aggregate just generated. And that puts it on an event bus, which is kind of the counterpart to the command bus. And that event bus can then just further provide these events to all interested parts of your system. And one of those could be an event projector, where an event projector is a term for an event listener that we often use to update the state in our database, which can talk to our read model repository to update the recipe itself, but maybe also counters for a dashboard or something. So that event bus and the recipe event projector just get an object that says, hey, this recipe was published, and then they can do their work accordingly. And what we can now also add in our system are other types of event listeners. Suppose we want to send notifications via email or social media or something when a new recipe is published that matches your filters or something. We can add another event listener that handles these notifications, right? That event listener receives a message, hey, this recipe was published, and then can send a notification to all users who are interested in that. We can also add a process manager, where a process manager is just a fancy word for an object that executes business processes by turning events into new commands. So suppose that every time a recipe is published or updated or something, all the ratings that people have provided for that recipe, they need to be reset. Well, we can add a process manager that just listens to the recipe changed event or a recipe ingredient added event or something, and then just calls reset ratings on some ratings object. Still, one problem of this architecture is that all the events in the system are volatile. You just, once you publish a recipe, you get a recipe published event, but after that event is handled, it's gone from the system. So we need to have all the correct event projectors right away to write our desired state to the database, to make use of that event. And also, if we have audit purposes, suppose people want to track all the changes to all recipes and who made them for legal purposes or something. If someone just put nuts in a nut-free recipe or something, they have to be sued. I don't know what business logic we have. It's difficult to get this from the system if all those events are just temporary. So, what a logical next step would be in this system is to apply event sourcing. And with event sourcing, the events are not just volatile in the system, they are stored, and even more, they are the single source of truth in the system. So only the events are the one thing that describes the entire state of the system, and all other information in the system is derived from these events. Well, what does such a single source of truth look like? We have our aggregate, and that plays a central role in enforcing all these business logic constraints and stuff. And they are responsible for all the previous events and turning new commands into either new events or exceptions or other things to indicate that some business constraint was violated. So suppose we have our recipe aggregate, and that aggregate already knows two events that we have stored in the system. Namely, one ingredient was added, one onion, and sometime later, 2 cloves of garlic were added to the system, to that recipe. And now we want to publish our recipe. So that recipe aggregate receives a call, hey, you should be published. And then it goes check all its business logic constraints. And it checks, hey, do I have any ingredients? Yes, I have at least one ingredient. Okay, that's fine. All my constraints are satisfied. And then it just provides a recipe published event. Hey, this recipe was just published. And that was okay. Suppose our second event is now not the addition of 2 cloves of garlic, but the removal of the onion from the recipe. So first we have one ingredient added, one onion, and then we have that same ingredient removed. If we were now to try to execute a publish recipe command, that recipe aggregate would see, hey, okay, so one of my ingredients was added and then removed again, so now I have 0 ingredients. I cannot be published with 0 ingredients, so it will throw some has no ingredients exception, for example. And in another case, when we have, onion and garlic, and then the recipe was already published, and we execute a new publish recipe command, hey, that recipe aggregate would know, hey, I'm already published. Why are you publishing me again? This cannot be. So it throws an already published exception. So this aggregate is responsible for turning the old events into state, checking new commands, new things that you want on that aggregate against that actual state, and then either denying that by throwing an exception, or allowing that by providing new events that arise from the new action, right? So that's how we arrive at an architecture like this. Instead of the write model repository now directly loading the state of the aggregates from the database, it just loads all the events from an event store, where all those events are stored. Then reconstructs the aggregate from that. The aggregate gets the call, hey, I want to publish you. It checks whether that's okay, and what events arise from that. And also that recipe published event originating from that publish call now is not directly put on the event bus, but it's first saved in the event store as the single source of truth for the system. So now our system knows, hey, this recipe was published, and it also provides that same event to the event bus for the rest of the system to update. So all the projectors can now also handle this recipe published event and update all those read models with the fact that that recipe was published. And maybe some read model for, maybe you have a separate database table for all the published recipes where only now that recipe is added to that table. Your event store could use SQL, as in this example, using a normal relational database. You could use a specialized event store. You could use a document database, anything you want. It's just a separate data store from the rest of the system. You could put it in the same database, but it could be separate. There are advantages of such an event-sourced architecture. One thing is that your event store now contains a log of the entire history of your system, every change that was made, at what time, by which user. So you could use that to build something like an audit dashboard. If you have legal requirements to know how certain things became the way they are now, using event sourcing, you can always show that to an auditor, how the stuff in your system originated. And maybe that's not really useful for a recipe website. But if you are doing stuff with legal, financial obligations, then you probably have restrictions around traceability of all these changes. Another advantage is that we can now do something known as reprojection. The part I have circled in green, we can execute that part of the system, that kind of a loop is in there. We can execute that separately. So if we have a big database migration or something, and we want to change the structure of a read model, we don't have to write a database migration to update all the data in those tables. We could just empty those tables, just get all the events that have occurred previously from the event store, rerun them through the entire event bus event projector loop, and then just repopulate our database based on the single source of truth, which were the events. Also, when we add a new event projector, suppose we build a system without the dashboard use case in mind, but sometime later we think, hey, we should add a dashboard. Yeah, we could fill the dashboard by just doing all kinds of SQL queries to gather statistics from the system and fill the dashboard. But we can also just add an event projector and a read model for our dashboard, and then just run reprojection by filling the dashboard using all the events we have saved, and we can just all execute those again. At the place where I work, we have one application where our clients wanted to have full time travel in their application, so they always wanted to be able to see the entire state of the system in the past. And when we built this for them, we chose an event source architecture, and we said, well, you're not going to get this from day one, because we didn't want to build the user interface and all the other stuff that was necessary to actually show this data to the user and make it available to them. But we promised them, from now on, if you start using this application, we can also always reconstruct the history that you want to see. And, well, about 3 years later, we could, just based on this event source architecture, could deliver this to them. We just added a new data structure which included temporary tables, temporal tables, to maintain data about when certain rows were valid and when they weren't, at what time in the past. We could just reproject the entire event store, and we then just had these tables filled, and the client could use all their information from the past. So, well, that's how we arrived at this big and complicated picture that I showed you in the beginning. So there's a lot more moving parts than we would have with CRUD. But we also gained a lot from all these steps that we took, right? Our business domain logic is now at the core of our code. We have decoupled stuff. We have added testability using unit tests. We have commands that convey clear intention and that we can decorate using a command bus to add stuff like transactionality, logging, queuing. We have specialized read models that we could add using specialized data stores optimized for the task at hand. We have process managers for distributed business processes. We could easily add in notifications in our architecture. We have auditability, and we could reproject our data for migrations and for new read models. So, is this useful? Well, it depends, as is always the answer. If what you're building is a simple recipe website and you don't have that complex requirements, you're probably fine with CRUD. If what you're building is essentially CRUD disguised as DDD, don't bother with all this stuff. Just stick to a simple CRUD architecture and you'll be much faster in making changes and developing that, because you probably don't need all of this. But if you need some parts of this, you can mix and match from the concepts that I've just introduced, and gather the benefit from them if you need them. So the main takeaway I want you to leave this room with is make informed choices for your architecture based on the needs your application has. If what you want or what you're doing is essentially CRUD, just use CRUD. If you use more complex domain logic, have more business requirements and stuff like that, need to add all these new functionality like event listeners and such, add an event-driven architecture. But know why you introduce things like that and make those changes informed. Right, that was it, what I was wanting to tell you. Are there any questions now? We have a microphone, yeah. I saw someone with a question all the way diagonally in the back.
Hi, thanks for a great presentation, by the way.
Thank you.
I have a question. What if, for an existing event, you have to change the structure? So let's say you have an event, you publish a recipe, but then a year later, you have to change the structure of the event. What happens to the events from the year before?
Yeah, that's a really good question, and that's something that a lot of people using event sourcing struggle with. I think there are two main approaches, maybe three. One is to add a new recipe published v2 event and then just forever support both the old and the new event in your system. You could use something that upcasts the event upon load. So when loading events, you just check some of them. Hey, this is an old event. I should convert it to the new event, and then you can support the new event. At the company I work for, we use an approach that is similar to the upcasting, but we already do it in advance on the raw data stored in the event store. We kind of have two event stores, one containing all the original events, and we have a structure that rewrites the original events to the modernized events, and that suits us fine.
Thank you.
Any more questions? Yeah, one in the back.
I was wondering about what are the benefits of using a command bus? If you can also use a dependency injection container to retrieve the commands.
That's true, but if all the command handlers are separate, you don't have a single place where you can decorate them using behavior that needs to apply to all the commands. So one of the advantages of a command bus is that you have one single point of, well, decoration in this case. All the commands go through one command bus. So if we want to add something like transactionality, logging, queuing, we could add it on the command bus and it would automatically apply for all the different commands. If we wouldn't have this, all these sources would talk directly to some of these command handlers. So you won't have the central part in the middle. And if we want to add logging, transactionality in such a case, you would have to add it separately on all the different command handlers, each of which has a separate API. They accept a different command, so that would be more difficult.
Check, thank you.
Any other questions? Yeah, one all the way in the middle.
I'm not sure if I missed that point, but if you're using the event sourcing, how does it impact the performance of reading, for example, a recipe? Because then, if I understood it correctly, you would basically have to rebuild the state of the recipe by executing all the events, or would you have a temporary table for the events?
Okay, so there are two places where you can read a recipe in such a case. You have, when executing your writes, let's see, okay. So you have here, your write model repository loads all the events from the event store and then reconstructs a recipe aggregate from those events. You could use something like snapshotting, like every 100 events, just store the state of the recipe aggregate, and then you only have to apply the events after that. So that's not really a problem, and often in most systems, it's okay if writes or changes are a bit more expensive than reads. And then you have your read model repository. which just receives the events if they have been executed and can just directly perform them on the database. Some people like to make somewhere here at asynchronicity. So they would make their event bus asynchronous and have this projector execute asynchronously. That would incur a small delay before the recipe can be found in the read model recipe according to the new state. But you could also do these events synchronously, and then it would just be instantly there. So I don't think there's really a performance overhead in this kind of things.
Okay, thank you.
Okay. So I think we're out of time for now. If you have any more questions, feel free to reach out using any of these mediums or find me here later. Thank you for listening.